Hello everyone, I'm Jiahao Zhang, a PhD student at the Australian National University. I will present RoMo, a large-scale, richly organized dataset and semantic taxonomy for human motion generation, built with collaborators from ANU, Roblox, Stanford, and Rutgers University. Text-to-motion generation converts language into realistic three-dimensional human motion, enabling prompts such as "a person dances hip-hop" to become usable sequences for games, virtual reality, humanoids, and visual effects. A major lesson from computer vision is that data scale matters. ImageNet scaled recognition and LAION scaled text-to-image generation. Text-to-motion still lacks comparable, well-curated data. Motion capture is accurate but complicated and expensive. Control studios and specialized equipment make it difficult to cover the long tail of real human activities. Our solution is to use internet videos as the data source. The key challenge is turning noisy web videos into reliable, high-quality, three-dimensional human motion while preserving real-world diversity. RoMo combines large-scale video collection, rigorous curation, and a semantic taxonomy from broad categories to fine-grained actions. The taxonomy starts with 54 broad categories covering fitness, sports, gestures, dance, communication, daily life, tool use, and many other domains. These categories are divided into 2,065 subcategories, giving each sequence precise semantic context instead of a flat label. We use the taxonomy to drive data collection with large language model assistance. ChatGPT synthesizes more than 58,000 search queries for diverse in the wild video retrieval. At this point, RoMo starts from more than 14 years of unfiltered video. Importantly, we do not simply scrape the web and release everything. The data must pass a strict taxonomy-aware filtering pipeline. During this final transition, there are three filters. First, the meta filter removes unsuitable videos using tags and descriptions. It rejects videos that are too short, below 24 frames per second, not about human action, not single person, unlikely to show the full body, or likely AI generated. Second, scene and human detection splits videos into continuous scenes and keeps clips with one visible moving person, removing cuts near static scenes, tiny subjects, close-ups, and truncated bodies. Third, the video and motion filter removes poor reconstructions and low-activity clips using adaptive motion quality signals such as dynamic score. The funnel is intentionally aggressive from about 125,000 hours of raw footage. Metadata filtering keeps about 66,000 hours. Scene and human detection reduces this to about 3.8 thousand hours. After video and motion filtering, only 1,237 hours remain. That is roughly the top 1% of high-fidelity human motion. After filtering, RoMo uses QN3VL for temporal semantic segmentation, slicing videos into atomic action spans instead of fixed-length windows. This avoids cutting through the middle of meaningful actions. For each action segment, GVHMR reconstructs word-grounded three-dimensional human motion from monocular video and converts it into the SMPL representation. This gives us reusable three-dimensional motion sequences for visualization, analysis, and training human motion generation models. RoMo also adds rich semantic annotations. Each sequence has detailed text descriptions and is mapped to category, subcategory, and atomic action labels, so the motion is connected back to the taxonomy. These examples show the final format: motion clip, detailed caption, and three-level taxonomy label. RoMo covers activities from barbell lifting and bowling to motion gaming and rafting. Overall, RoMo contains more than 820,000 motion clips and 1,237 hours of data, organized into 54 categories and 2,065 subcategories. Compared with Motion Million, RoMo provides stronger motion dynamics, achieving a 41% higher dynamic score after filtering static and low-activity sequences. RoMo also improves semantic coverage by 61.7% at the subcategory level, with broader caption diversity in embedding space. We train modern motion generators on RoMo and evaluate text alignment and physical quality, revealing strengths of both diffusion-based and GPT-style models. We also released the Motion Toolbox with browser visualization, unified benchmarking metrics, and conversion tools across common motion formats and datasets. In summary, RoMo contributes a large-scale filtered motion dataset, a rich hierarchical taxonomy, and open tools for reproducible motion generation research. Thank you.